another definition that we will see a lot in fluid mechanics, and actually this is a very important definition and a very important tool in fluid mechanics and fluid dynamics in general. It's called the material derivative, or the total derivative, and sometimes it's called the substantial derivative. What is meant by a material derivative? What's meant by the total derivative? What's meant by the substantial derivative? Okay, let's tell the story from the beginning. I have a fluid particle. This fluid particle moves with a velocity vector. This velocity vector has three components: u, v, w. And this velocity vector is in a certain flow domain with other fluid particles moving also in the domain. Okay, let's zoom on this particle and try imagine yourself sitting on the particle and feel what the particle feels. The particle at this location, let's say this location is X node, Y node, Z node. And at the time, at the point we start to observe the particle is T node. After an infinitesimal distance in a certain direction, the particle is now here. So it has moved by a distance dx in the x direction, a distance dy in the y direction, a distance, sorry for the pen, dz in the z direction. And at the same time, a time has elapsed that's equal to dt. So we want to know at the new location, which is distant by dx, dy, dz from the old position, and after time delta t, what is the new temperature here? So the particle had temperature at this point, T1, and at the new location, the particle has a temperature that could be different from the temperature at the old location. So the material derivative, or the total derivative, or substantial derivative, all the three names refer to the same thing, can calculate the new temperature. Actually, it doesn't calculate the new temperature. It calculates, you have a temperature here, and you have a temperature here that is different from the old location. If you subtract the old temperature from the new temperature and divide this by the time, you will have the change of temperature with respect to time. But the problem is the temperature as a function, could change with x, y, z, and t. So this derivative is not obtained only by just computing the derivative of the temperature with respect to time, because the flow could be steady, which means that the temperature doesn't depend on the time, which means that at this location, the flow has a certain temperature that doesn't change with time because the flow is steady. And at this location, the flow has a certain temperature that doesn't change with time, but the temperature at this location is different from the temperature at this location. So when the fluid particle moves from this location to this location, and I am using my stopwatch, I will see that with time, there was a change in the temperature, and so I can't say that the temperature hasn't changed with time, despite that the time doesn't exist in the temperature definition. For example, in a steady flow. So the material derivative addresses this problem. How it addresses this problem? It says that if you want to find how does the temperature change it with time for the fluid particle as it moves through the flow domain, you have to calculate a lot of gradients. The first gradient is that you calculate partial T, partial the temperature, partial time. So for example, I have a temperature that is equal to X, Y, Z, T. T is the time. So you differentiate this equation with respect to time. And this is the partial T, partial T. And also, the temperature could change with the X direction, could change with the Y direction, could change with the Z direction. You calculate each gradient of these gradients, partial T, partial X, partial T, partial Y, partial T, partial Z. If you look at partial T, partial X, if you multiply partial T, partial X by the U is the velocity component of the particle in the X direction, which by definition is equal to dx by dt. When you multiply U by partial T by partial X, you calculated the change in the temperature with time that arises due to a change in temperature with location, not a change with temperature with time in its main equation. So overall, when you want to find the total temperature change with time, you calculate its derivative with respect to time and with respect to the space coordinates. And regarding these components, you multiply each derivative of these with the respective velocity component. So finally, the total temperature derivative with time is calculated from this relation, partial T plus U partial T partial X plus V partial T partial Y plus W partial T partial Z. And the same thing, the same methodology could be applied for any variable Q. Instead of temperature, you may want to find the total change in the density, for example. So instead of the temperature here, you put the density. So the equation will be partial rho partial T plus U partial rho partial X plus V partial rho partial Y plus W partial rho partial Z. So this equation accounts for the change of the variable with respect to time and the change of the variable with respect to the space coordinates in order to find the total change of the variable We are considering with respect to time. This this is from the viewpoint from the viewpoint of an observer sitting on the fluid particle as it moves through the flow domain and try to measure the changes in the properties like the temperature, like the density, the fluid particles encounters as it moves through the flow domain. Okay. The same concept could be applied to the velocity. If I want to find the total change of the velocity with respect to time, this is called the material derivative of the velocity. And from our background, the change of the velocity with time is the acceleration. So the total derivative of the velocity is the acceleration vector. So instead of the temperature, instead of the density, you will put the velocity vector. So you have partial v partial t plus the changes in the velocity with respect to the space coordinates multiplied by the respective velocity component to account for the effect of velocity change from location to location. And we multiply by the velocity to kind of ensure the dimensional homogeneity of the equation. The term representing the term partial v partial t represents what is called the local acceleration, which is a change in the velocity with respect to time. The change considering the velocity changes with the space coordinates is called the convective acceleration. So the total acceleration of a fluid particle is the sum of the local acceleration and the convective acceleration. The concept of total derivative or material derivative is a new concept that you may encounter here for the first time. Okay, this is another definition and another concept that we need to highlight. Okay, let's see another thing. The motion of a fluid particle. Let's talk about the kinematics. I have here a reference frame XYZ and a fluid particle, an infinitesimal fluid particle that is moving in the flow domain. After a certain time, the fluid particle is at a new location, and we can see here that the shape of the velocity vector of the fluid particle has changed. In other words, it deformed. Some deformation occurred to the fluid particle as it moved through the flow domain. And deformation could take many shapes. For example, here, the fluid particle, its original shape is the shape that is shaded. After a certain time, we see that the flow particle has elongated. The elongated shape could be at another location, but here in this slide, he just puts the two shapes on each other in order for you to distinguish the difference that occurred in the shape of the fluid particle as it moves through the flow domain. So here, the kind of deformation that happened is longitudinal deformation, which means that the angles between the lines didn't change, but it has elongated in a certain direction and shrank in another direction. This is called longitudinal deformation. Okay. For example, let's in the x direction here, the length is delta x. After a certain time, the length increased by a certain amount. If you divided the change in the length with respect to the original length, then you have found the strain. And if you divided that strain to the time that elapsed from the original location to the new location, then you have calculated the strain rate. In fluid mechanics, we are more interested in the strain rate other than the absolute strain. So here I have a longitudinal strain rate. Here we can see that the angles between the lines have changed. So this kind of deformation is called angular deformation. The fluid particle could deform longitudinally, could deform by angular deformation. Both types of deformation can happen together. It could linearly deform, and it could also deform by angular deformation. Both types could happen. A single type of them could happen. All the drama exists. Okay. Besides that, the fluid particle could just be displaced from one position to another position without having any deformation in its shape. So in this case, I'm considering only a translation of the fluid particle. Or it could rotate around a certain axis without deformation. This is called a rotation. So as the fluid particle moves in the flow domain, it could experience translation, rotation, angular deformation, linear deformation, or all of these things could happen. Okay. We will know later, we will learn later that these deformations, whether linear or angular, and even the rotation of fluid particles, are functions of the velocity gradients with respect to the space coordinates. And this will be explained in detail when we solve the problems on this chapter. Okay. So these are the main concepts and definitions that I want to discuss with you in chapter 1. And this brought us to the end of our section today. This week on Tuesday, we will have a face-to-face section at the department. I hope that you will all attend to solve the problems and to answer any questions that you have regarding what we have explained in this session. So thank you and see you soon. Take care. Assalamu alaikum wa rahmatullahi wa barakatuh.